In the previous session, we discussed about the epimerism and epimers. In this session, I'll be taking up the anomerism. The objectives of this session are, at the end of the session, the learner shall be able to describe what is anomerism and what are anomers. Okay, the second objective is mutarotation. Before knowing about anomerism and anomers, let us discuss about the intramolecular arrangement in an exosugar. The intramolecular arrangement in an exosugar takes place between the aldehyde or keto group with the alcohol group. Let us first take up the aldoses. Okay, let us see here the aldehyde group. I am writing here. Okay, and then here. Okay, then these two, they can react and leads to formation of hemiacetal. Leads to formation of hemiacetal. Okay, the linkage between aldehyde and an alcohol intramolecular arrangement, it is what we call hemiacetal. Okay, then let us see about the keto group. Let us see about the keto group. The keto group, the linkage, we call it the hemiketal. Let us take up the a ketone group. Okay, this is ketone group which is present in fructose. Okay, then it reacts with the alcohol and then it leads to the hemiketal. Okay, see how the hemiketal formation is taking place. How the hemiketal formation is taking place like this. So there is hemiacetal formation and hemiketal formation has taken place. Now I will write straight chain exose sugar structure and also cyclic structure. This is the straight chain structure of glucose. Okay, glucose. So there are 6 carbons. Out of these 6 carbons, 4 carbons are asymmetric carbon. There is a possible 16 isomers. The linkage takes place intramolecular. The linkage taking place between carbon 1 and 5th. Okay, then when you see the cyclic structure, in the cyclic structure, there is the 5th carbon. Once the first carbon also becomes the asymmetric carbon, the first carbon we can say symmetric carbon. This carbon we call it anomeric carbon. This carbon we call it anomeric carbon. The first carbon, anomeric carbon. Okay, so the configuration around this anomeric carbon, there is a difference between two anomers. If you take the first one, here it is the hydroxyl group is below the plane of the ring, whereas here the hydroxyl group is above the plane of the ring. Above the plane of the ring. Okay, you can focus it on here the hydroxyl group is below the plane of the ring, and here hydroxyl group is above the plane of the ring. Okay, so there is a more distance between CH2OH and OH, and here less distance between CH2OH and OH. Okay, then the next one is this one. In this particular anomer, the first one we call it alpha D glucopyranose. Okay, this is called beta D glucopyranose. Okay, pyranose. So what happens? The anomeric carbon becomes a asymmetric carbon. So then what will happen? So instead of 16, we get 13. Instead of 16, we get 32 isomers. 32 isomers, including the anomers. Okay. The same thing with the fructose. Same thing with the fructose. You can see below the plane of the ring, this is the first carbon. This is the first carbon. This is the above the plane of ring. Okay. This is the first carbon. Okay. Then again, let us see here. Let us identify like this. Okay, like this. Okay. So this is what we call it. We call it this one is alpha D fructofuranose, and here beta D fructofuranose. Okay. So this is about the anomers, how the anomers formation takes place, how many isomers they are possible. How many isomers they are possible. Okay. Now, let us talk about when these anomers, the specific optical rotation of one anomer is different from the other anomer. Specific optical rotation. The specific optical rotation that is represented like this. The specific optical rotation of one anomer is different from the other anomer. Suppose if you take the alpha D glucopyranose, its specific optical rotation is plus 112 degrees. This can be converted to beta D glucopyranose. Beta D glucopyranose. Its specific optical rotation is 18.17 degrees. Okay. Well, in the solution, the alpha D glucopyranose, during the interconversion, first attains the acyclic form. Acyclic form, that later, again, you can see here, it is converted to beta D glucopyranose. Beta D glucopyranose. Okay, this is plus 18.7 degrees. Here it is 112 degrees. Okay, so based on that one, we can describe mutarotation, the second objective, mutarotation. Okay, we can describe the mutarotation. In the mutarotation, it can be defined as the change in specific optical rotation representing the interconversion of alpha and beta forms of any exo sugar of D-glucose. Okay, so what happens to up to what extent? To an equilibrium mixture. Mutarotation is the change in specific optical rotation representing the interconversion of alpha and beta forms of D-glucose to an equilibrium mixture. Suppose, let us see here, we'll take up alpha D glucopyranose. So that is converted to beta D glucopyranose. Like this. Pyranose. Alpha D glucopyranose and beta D glucopyranose. So at equilibrium, suppose at equilibrium, the specific optical rotation will be around plus 52.7 degrees. Okay. So at the equilibrium, there will be 36% alpha D, okay, alpha D glucopyranose, okay, then 63% beta D glucopyranose, That means there will be 1/3 of alpha D glucopyranose, 2/3 of beta D glucopyranose at the equilibrium, and 1% will be in acyclic form. That means most of the hexose sugar, it will be in the beta D glucopyranose. Okay. Then, so suppose if you take the fructose, the specific optical rotation, optical rotation at equilibrium is around minus 92 degrees. Will all the sugars show mutarotation? No. Non-reducing sugars like sucrose, they do not show the mutarotation. So there is no free aldehyde or keto group. Okay, they do not show the mutarotation. Okay, then what is the importance of knowing about anomerism and anomers? Suppose in the biochemical lab, a solution of glucose is prepared to use as standard that cannot be immediately used because most of the glucose is in alpha D glucopyranose form. It shall be allowed to be converted to beta D glucopyranose, reach the equilibrium mixture, because enzymes which are being used, so they will be specific for the beta D glucopyranose. So if you use immediately, so standard values will not be correct. That is the reason as far as the clinical laboratory is concerned. Other aspect is enzymes, they will be either specific to the alpha D glucopyranose or beta D glucopyranose. Okay, this is about the anomers and anomerism. Now I will summarize. Okay, I will summarize. In this session, I have taken up anomerism and anomers. Okay, anomerism and anomers. Okay, objectives of this session are, at the end of the session, the learner shall be able to describe anomers and anomerism and mutarotation. Before going into the anomers, we have taken up how hemiacetal or hemiketal formation has taken place. Okay, then we have written the straight chain structure of the glucose and showing that there are 4 asymmetric carbons are there, so 16 isomers are possible. Then we said there will be linkage between carbon 1 and carbon 5. Okay, then leading to the cyclic structure, so that is alpha D glucopyranose, beta D glucopyranose. So the configuration around the anomeric carbon, OH is the below the plane of the ring, whereas hydroxyl group is above the plane of the ring. Okay, then because of these anomers, so instead of 16, 32 isomers can be possible. They are possible. Okay, then we also talked about alpha D fructofuranose and beta D fructofuranose. Okay, then we have discussed about specific optical rotation. Okay, then alpha D glucopyranose is having plus 112 degrees, whereas beta D glucopyranose plus 18.7. They can be interconverted. So first attaining the acyclic form, then into another form. Okay, then next we described about the mutarotation, the change in specific optical rotation. Okay, representing the interconversion of alpha and beta forms of D-glucose at equilibrium mixture. So that is what we said about the mutarotation. So here alpha D glucopyranose converted to beta-D-glucopyranose. At equilibrium, the specific optical rotation is plus 52.7. At the equilibrium, there will be 1/3 alpha-D-glucopyranose, 2/3 beta-D-glucopyranose. Only 1% will be in the acyclic form. We also talked about the fructose. It's the specific optical rotation at equilibrium. Then, so non-reducing sugars, they cannot show the mutation because there is no free aldehyde or keto group. So that is the reason they cannot show the mutation. The freshly prepared standard solution, so the most of the glucose is in the alpha D glucopyranose form, and later it will be converted to beta D glucopyranose. Before using the standard, it shall be allowed to reach the equilibrium. Okay, sometime it shall be kept so that the results of the standards will be correct. Okay, so because the enzyme which is being used for the investigation purpose, it will be specific for the beta D glucopyranose. This is about anomerism and anomers. In the next session, we will discuss about the derivatives of hexoses and pentoses. Okay, thank you very much.